Okay, now let's start our new class today. So in the previous class, we have left one question for you, a problem to solve. Did you get your answer? So let's go through the solution together and see if you're right. So first of all, you have an infinite plane of charges. Let's suppose it's a positive charge. And first we can, now the question is, what is the electric field strength at some point? Let's say here at this point, what's the electric field? So first of all, let's try to use Gauss law to simplify the calculations. The key is to make a Gaussian surface which has a perfect symmetry, which can help us to solve the problem. What we can do is let's first make a cylinder which goes through and perpendicular to this plane, so that you have a side surface and two ending surfaces. Those two end surfaces, if you choose it perfectly, they should be the same distance from the plane, so that it's in a perfect symmetry. On the left side, you have E going to the left. On the right side, you have E going to the right. And then let's check the field lines. So first of all, are there any field lines go out of the side surface of the cylinder? No, they should always, the field lines should always be perpendicular to the plane, which is parallel to the side surface. So there's no field lines going out or going in to the side surface, which means the flux of the electric field on the side surface is 0. And then the flux on the two sides or the two end surface could be calculated as E times dA. And then the flux of the entire cylinder closing surface or the cylinder Gaussian surface could be calculated by 0 on the side plus E times A, which is this area, plus E times A, because at both ends the electric field are going out, which is the same direction as dA. Cosine theta is 0, cosine theta equals to 1, theta equals to 0. And then you can do the integral to calculate the flux of electric field. It becomes a very simple. It's just the surface area times A times E plus surface area times E. And then let's talk about the charge, which is the other side of the equation. For the net charge, suppose you have this charge density to be, let's say, eta. Then eta equals, then the net charge equals to eta times this area, which is the same area as the tip of the cylinder. Okay, so the flux is 2EA, is the electric field, A is the area. And the Q equals to eta times A. This area, this circle area A is the same as the circle area here. And then flux equals to Q over epsilon. Flux is 2EA, Q over epsilon is eta A over epsilon. And then you get this equation, and finally E equals to eta over 2 times epsilon. Is that your answer? Okay, great. From this equation, we can see if the electric of infinite charge, if the electric field line on the infinite large charge the plane, then the electric field is a constant. It's independent from the distance. So no matter it's close to the plane or it's far from the plane, the epsilon is the same. So it's also intuitively shown, because if we look at the electric field lines, they're parallel to each other, right? Because it's an infinite big plane, they can't cross to each other. They have to be parallel to each other. I have an example here. So when it's parallel to each other, then the density of those lines are always the same. When the density is the same, the strength of the field lines should be the same, because closer field lines or denser field lines means stronger electric field. If they're parallel, then it should be a constant. Thank you. Thanks. Seems like they're holding a party, maybe. Now let's see example shown here. A cylindrical Gaussian surface surrounds an infinite line of charge. The flux through the two flat ends of the cylinder is which option is your choice? Okay, now let's see. So who is going to choose A or B or C or D? Okay, so first of all, what's the direction of the field lines? It's a radial direction from the wire or cylinder. Okay, then it's always going out, right? It's always going out. And we're asking the flux through the two flat ends. Those field lines, they're always going out and perpendicular to the wire or cylinder. Then the two end surface, they're also perpendicular to the wire. So your surface, your end surface is parallel to the field lines. Then answer is 0. There's no cross, no field lines cross or go through the two surfaces. What about this one? Let's say the electric field at the surface is E. Then what's the answer? Okay, let's try. So who's going to choose A or B or C or D or E? Okay, so it's B. So let's say the strength of the electric field is E. Then E is always perpendicular to the surface, the side surface, right? When they're perpendicular to the surface, that means the direction of the E is parallel to the direction of your surface or normal direction of the surface. Then cosine theta equals to 1. Then the dot product of E and your surface area A becomes simply E times A times cosine theta. Cosine theta is 1, so it's E times A. So what is A? So the circle, the length of circle is 2 pi r, and then the length of the cylinder is L, so it's 2 pi r L, which is A times E. So you get your flux. Okay, let's do simple calculations. Now let's see some features in conductors using the Gauss laws theory. So here is a figure which show a Gaussian surface inside the conductor's surface. Let's say this black line shows the shape of the conductor. In the conductor, you have a red line or red surface, which is an imaginary surface, which is a closed surface. Therefore, it can be considered as Gaussian surface. So first of all, what's the electric field inside? Or what's the electric field at the surface? At any surface or any position inside this conductor? It should be 0. Because E is 0. Because the Q is 0. There's no charges, net charges inside a conductor. Why? Can there be some charges in the conductor? No. Why? Let's say if there is, what will happen? Let's say if there is a distribution of several positive charges inside a conductor, what will happen? Yeah, they will move. Move to where? Right, to the surface. They have to be moved to the surface because they repel each other. When they repel each other, they are trying to get as far as possible with each other. So the furthest place they can go, first of all, they cannot leave the conductor because in the conductor there are some atoms with nuclears, which is a positive, so that the and some electrons are negative, so that the positive charges and negative charges they cannot leave away from the conductor. Therefore, they have to be on the very surface of the conductor so that they get very far away from each other. So for a conductor, inside the conductor, there shouldn't be any net charges. If there is, then that's not a conductor. The definition of a conductor is inside this material, the charge is free to move. So there's no charges inside. Then let me first clean the slides. Then if you want to calculate the E here at any position, let's say here, Let me clean it. If you have one point here, E, you want to calculate the E here, what you can do, you can draw any arbitrary surface here. You know, inside the surface, there shouldn't be any charges. Net charge is 0, therefore the flux is 0, then the E should be 0 and at any place. So the conclusion is for a conductor, the Q inside is 0, the net charge is 0 inside, and the electric field is 0. What about on the surface? On the surface, what's the direction of the electric field? First of all, don't look at the figure. Look at my hand drawing picture. This is, let's say this is part of the surface of conductor. Is it possible the field line going in this direction? Is that possible? Exactly. Why? If it's not perpendicular, what happens? They will move. They will not be equilibrium, right? So for example, if E is in this direction, then you can decompose it into two components, perpendicular and along the surface. It has a component of along the surface. Then if you have a charge here, it will simply move because you have a component to push it on the from one side to the other side on the surface, it will move.
So is that because like those perpendicular components, they do exist, they cancel?
You mean
like in that surface, there was just right next to it, there would be another charge, but also kind of pushing the opposite.
You can also think in that way. The charges, they're smart because they're free. So they will free to move. And then finally, you can think about at this position, there are a lot of charges here and also on the right side and also on the left side. Finally, there will be a balance or equilibrium so that the left effect and the right effect, they balance each other so that the electric field is perpendicular. Otherwise, the charge will move and adjust the field lines until the field lines are perpendicular to the surface so that they have no any forces to push them to move. So that's a equilibrium state. When the charges are equilibrium, then all the field lines are perpendicular to the surface. So here, let's say the external electric field line right at the surface of conductor must be perpendicular. If it were to have a tangential component, it would exert a force on the surface and cause a current or a motion of charges. And the conductor would not be in electrostatic equilibrium. So that's another feature of conductor. Okay, one more interesting feature for conductor is the magnitude of the electric field. So first of all, the direction of the electric field is interesting. It's always perpendicular. Then the magnitude is also interesting. Let's see what happens to the magnitude. First, let's calculate it. Here, if we have a conductor shown in this way, and we want to calculate, let's say, the electric field outside the conductor at this position, then what we can do is a Gaussian surface extending through the surface of a conductor has a flux only through the outer surface. So we can draw a Gaussian surface, which is a cylinder, and it's perpendicular to the surface, and then it goes through the surface. So that if your, let's say your Gaussian surface cylinder is small enough, then all the field lines are in the same direction of the area direction of your surface direction. They're in the same direction. They're all perpendicular to your conductor surface. And then again, what's the flux at the side? What's the flux of the side surface of the cylinder? At the sides, yeah, at the side of the cylinder, it should be 0. Why? Because your cylinder, if you do it perfectly or correctly, your cylinder should be perpendicular to the surface. And you know, at that point or position, the field line is also perpendicular. That means there is no field lines going out or going in to the side surface. Then that's 0 for the side surface. Flux is 0. Now let's talk about the flux on the two ends of the helix. So first of all, here on the outer end, let's say the flux should be the area, which is A times E. And then the inside flux, what's the flux of the inside end surface? Zero. Why? Yeah, but another point is if you do the EA or calculate the flux at the end surface, which is inside the conductor, A is the area that you can calculate. What is E? 0. As we discussed here, inside a conductor, the E is always 0. So at this tip, or at this end, the flux is 0. Inside, it's 0, and on the side surface, it's 0. Only at this outside end surface, it's E times A. Then E times A equals to Q over epsilon. How to calculate Q? Q is the charges on this piece of area, which is eta times A. Here, Q equals to eta times A, which is a surface area here times the density of eta. And then if you plug Q equals to eta times A in this equation, you will have E surface equals to eta over epsilon. So that's the solution of electric field at the or close to the surface of a conductor. That's interesting because you will see the first of all, the electric field on the conductor, it's independent of the position. No matter where it is, once the charge density is known, you will know the electrostatic, you will know the electric field surrounding this conductor, no matter at which position, no matter it's here or there. And also, it's independent from the distance, right? If it's close to or a little bit far away from the conductor, the electric field is the same. As long as you can consider the conductor is big enough or your distance is smaller enough. I mean, the distance from your testing point to the conductor is smaller enough so that you can do a Gaussian surface in this way. If it's too far away, you can imagine if the conductor is very small, distance is very far, it's almost impossible for you to draw a Gaussian surface perfectly in that way, because you will contain the curvature, which is no longer a surface or a flat surface or a planary surface in this calculation. But as long as your testing point is close to the surface of the conductor, then the electric field is a constant. Okay, so now let's see this question. Let's solve it and see what is your best answer. So what is your answer? You need some time to do the calculation? If you need, then you're wrong. Okay, so first of all, can we use Coulombic equation to solve the problem? Hmm? So first of all, actually, we can't use Coulomb's law because in what conditions can we use Coulomb's law? Coulomb's law is true, but it's under some specific condition. First of all, the two charges should be point charge. They're very small. If there are two sphere or one sphere and one arbitrary object, then Coulomb's law is not the equation to describe the interactions between such projects. They have to be point charges. Second, the distance should be far away. Let's say if you have a sphere and you have a square, if they're very far, they're far away from each other. If they're very far, you can still use Coulomb's equation or Coulomb's law to do the calculation, because you can now approximately consider each object to be a point charge when they're very far away from each other, of course. And another very important thing for the Coulomb's law is the dielectric feature, or the epsilon, because when you use Coulomb's law, you have Q1, Q2 over 4 pi r squared epsilon. But if you put a charge and another charge in a non-uniform epsilon, then Coulomb's law doesn't work. Coulomb's law has epsilon there. It has single epsilon here, means when you use Coulomb's law, it has to be in a single epsilon material, which is homogeneous material. But in this case, let's say Q1 is in vacuum or in air, but Q2 or your test point 2 is in metal. So they're in different materials. So in this time, in this case, the Coulomb's law cannot work. But what we do know is it's a metal. If it's a metal, what will happen? There will be some induced charges on the surface. So if there's a way that you can calculate how much negative charges are induced on the left and then how much positive charges on the right and what are the distributions, then you can use Coulomb's law, because now you can substitute the effect of the material of the metal object instead of those charges. You can replace the metal by putting some fixed charges if you know the distribution. But that will be very complicated. The simplest thing we can do is, now we want to calculate here. We want to calculate the E here. So first of all, is there any charges here? No, it's in the, yeah, it's in the conductor. So as we learned, for conductors, there shouldn't be any net charges inside. If you draw a surface, a Gaussian surface, here, or there, or there, no matter which Gaussian surface you draw, there shouldn't be any net charges. Then what's the electric field at that point? It should be 0. So the conclusion is for a conductor, once you put it in an electric field, the inner electric field is always 0, no matter what is the external electric field. And it's in this example, it's a sphere. What about it's not a sphere? If it's a square, what happens? The same thing. So no matter what shape it is, you will always have 0 inside. Okay. Equilibrium of conductors. So here, this figure shows a charged conductor with a hole inside. Since the electric field is 0 inside the conductor, we conclude charge is 0. And furthermore, since there is no electric field in the conductor and no charge inside, the electric field in the hole must be 0. Okay. So we're now talking about making a hole in a conductor. If there is a hole, still the charges are distributed on the very outside of the surface rather than the inner surface, which is the surface of the cavity or the hole. So still, if you make a Gaussian surface here or here or here, you might make Gaussian surfaces, it will not include any charges. And then the net charge inside the hole is always 0. And inside the surface of the cavity or hole is 0. And the electric field lines are also 0. Faraday cages. Okay. So now we have introduced some features of conductor. So now you have seen the conductor can screen the external electric field. In this example, you see inside this, let's say, metal or conductor, the electric field should be zero no matter what is outside or external electric field. So that's a screening. So the conductor screens the electric field by the induced charge, so that inside the metal or inside the conductor, the electric field is zero. And then even there's a hole inside, the conductor can still screen the external electric field. Since even there's a hole inside, it can screen the electric field, then why not we make the hole big, so that in many cases when we need to screen the external electric field, then we can make it by simply making a very big hole in a big conductor. Then what's that? That's a cage. So for example, now if you have external electric field, it might be generated by any source. For example, the parallel plate capacitor, it might be the source of generating such a external electric field. When you put object, first, if you put a solid object, which is a conductor, then you know inside the conductor, the electric field is zero. And if it has a cavity, you know inside the conductor and inside the cavity, the electric field is zero. Then we can make a cage. It could be in any shape. For example, it's a cube. If you make a hollow cube, which is a cage, if you put the cage in the electric field, in the external electric field, then inside the cage, your electric field should be zero. Then we can utilize this feature to screen electric field. And later on, we will learn not only electric field, but also other signals can be screened. For example, if you put your phone in a metal cage or metal box, then the box will screen the signal, because the signal of your cell phone or any other wireless signal, there's simply some effect of electro and magnetic signals, so they can be screened. So here, this figure shows a charge inside the hole within a neutral conductor. Okay, now if you have a charge here, then we know for a conductor, the charges are free. There will be some induced charges on the surface of the cavity, and also some charges on the outside surface. If you put a charge Q here, the net charge, negative Q, moves to the inner surface or the surface of the cavity, and the plus Q are on the further surface. So that when you do a calculation of E inside the metal, you will still have E to be zero, because when you make a surface, Gaussian surface, no matter which way you do it, you will have zero charges, zero net charges inside the closed surface or Gaussian surface. No matter you make it this way or this way or any arbitrary way, as long as it contains the cavity and the charge inside the cavity, then the net charge to be zero. Then the electric field inside should be 0. That's another type of screen. So the previous Faraday cage, it screened the external, let's say, electric field lines or external electric field, so that inside the cage, there's no electric field. But here, it screened the electric field from the cavity, so that inside, the conductor, the E is always 0. Therefore, outside the conductor, the E is also 0, right? Is that right? Let's say if you take a point here and try to calculate the E should be 0 if in the conductor. If you calculate the point here, the E should be 0, right? No. Is it 0? No, because if you make surface, let's say any surface here, this time, if this point is out of the conductor, then what's the net charge inside? That's the net charge, Q. Inside the cavity, inside the metal, you're not including those surface charges, those plus or positive surface charges at the outside surface. That's why you get 0 charge, net charge in the Gaussian surface, which is inside the material or the conductor. However, if it's outside, then the net charge shouldn't be 0. The net charge should be Q. Then the E shouldn't be 0. The E should be something in this direction. Okay. Let's take a quick look at this checking question. So which option do you think is right? Okay, let's see. So are you going to choose A or B or C or D? Okay, what about another question? Now let me change the question to be the total charge on the inner surface of the metal is what? It should be so first of all, I think we all agree inner surface is negative, outer surface is positive. And it's a metal, it's a conductor, so that there shouldn't be any E or electric field inside. Otherwise, if there is an electric field inside, the charges will move. It's a conductor. Now it's equilibrium state, no charge is moving. That means if you draw a surface of Gaussian here, the net charge should be 0 because no matter which way you draw the surface, the electric field at any position should be 0. Simply means inside the surface, you have 0 net charge. And here you have +3. That means on the surface, you should have -3. Okay, now you have -3 on the inner surface. And the metal is neutral. That means all the plus or positive 3 charges should be distributed on the other surface, which is outer surface. Then the answer should be B. Okay, let's see one example. A 2 centimeter diameter brass sphere has been given a charge of this much. What's the electric field strength at the surface? So now you have sphere, and you know the charge is 2, let's say, nanocoulomb. And then you're asked to calculate the E at the surface. So first of all, what's the direction of the E? It's a perpendicular to the surface or normal surface. If it's not perpendicular, then this is a brass sphere. It's a conductor. If it's not perpendicular, the charge will move. It won't stop moving until the electric field doesn't have any tangent component, which means at any point on the surface, the electric field is perpendicular to the surface. And then that's the direction. So first, direction, second, the magnitude. How to do the calculation of the magnitude? You can simply make a Gaussian surface, which is exactly the surface of the sphere. It has a perfect symmetry. And then you know the net charge in your surface is 2. And then you can use Gauss law. Okay, so here it use another way to do the calculation. But if you want to use Gauss law, you have Q over your epsilon equals to your flux. How to calculate the flux? It's E times A. A is the surface area of a sphere. How to calculate that? Right, so 4 pi r squared, you know the A, and you know Q, you know epsilon, then you can calculate E. This is the first way of solving this problem. The second way is first calculate the density, which is eta on the surface. Then use our previous introduced equation of surface electric field, which is eta over epsilon. So here it used the second way. First calculate the eta, charge density, because you know Q, you know A, can calculate eta, and then we can simply calculate it using the equation here. Okay, so that's the summary of everything for Gauss law. Using Gauss law to do the calculation is easy. The most important step is to find the Gaussian surface. If you make a Gaussian surface in a perfect way, it will simplify the integral in a simple calculation, such as a surface calculation of a sphere, a surface calculation of a cylinder or something, which will make your calculation very easy. Okay, that's it for the uh, Gaussian surface or Gauss law. Do you have any questions? If no questions, then that's it for today's class. I will share a homework with you. It's a couple of questions for using Gauss law to do some calculations. Okay, I'll send you the homework either tonight or tomorrow morning.